At terminal velocity, terminal speed, we're going to have a look at this idea about can things reach a maximum velocity when falling to the earth. Well, the way it's talked about at GCSE is that we have an aeroplane, and apologies here to all plane manufacturers, and we throw somebody out and they start to fall. And if we have a look at the graph of their system, it goes up and then gradually reaches what we call terminal velocity. That's about something like about 100 miles an hour, which is not going to do an awful lot of good. So what people typically do is they open up a parachute and what happens is suddenly when you're watching someone, they fly upwards. They don't, it's just the other person slows down dramatically and their speed slows down dramatically until they reach a new terminal velocity. Well, that's not going to be really practical to do here. Oh dear. It's the hay fever season, and what I'm going to do is I'm going to take a long tube, and this long tube we're going to fill with a liquid. Now, in the past I've tried various different liquids. Today I'm going to try something boring. I'm going to actually try water. We'll see how accurate the machine is that we can actually use to do this. And what I'm going to do is, having filled this with water, probably an idea to put it in a bucket, then I'm going to take a small mass and I'm going to drop it. I'm going to see if it will accelerate up to a speed and then stay at that speed. Since it's going in one direction, let's say it's going to have a velocity, and we're going to have our velocity at the start is going to be u, and I'm hoping somewhere about some way down it's going to keep a velocity v, and that is going to stay constant, and this is going to be our terminal velocity. Now, I've seen a whole load of ways of trying to measure this. One of the better ways is if you fill that tube up with something like wallpaper paste, make it really quite viscous, and then you drop weights in there, then you can measure constant times and measure the distance, and you put rubber bands around it and you try and show that the rubber bands get to be the same length. Well, we're going to try a bit more upmarket technology. There is another way of doing this experiment, and I'm not terribly impressed with this one, and that is to use a ticker tape timer. And what's suggested is you take a ticker tape timer, maybe one that some people are familiar with and not others, and this takes a piece of very thin paper and it goes through the ticker taper timer. It measures at 50 Hertz, and so we have this going up over a pulley and then going down into the tube, which is full of liquid. So this is my ticker tape, and that's attached to my mass, which is in water.
Sorry, I couldn't find a contact.
Alexa,
in water.
Alexa, stop. Right, so this is then some sort of viscous liquid, and if you arrange this correctly, then with this paper freely flowing, hopefully when it starts you don't get too much of this paper wet, because once it goes in there and it gets wet, it's very difficult to try and deal with. We're going to do something similar, and I've got a partial setup already done so that we can have a look at what's going on. Now, if we're going to look at our system, we've got to have some idea of what we're going to try and measure, and so we can look at some sort of force here going on, and we can have a look and see what's making some sense. So we can try and work out various things like suvat. We can measure some of those things, and we'll decide what we want. What we can also guess on is something here about D, which we're going to call the drag force. And if we look at the acceleration going down through one of these, we normally say here the initial drag force when we start is going to be 0, so we can get a formula that G equals D over M, and we can say that's going to be our acceleration. Well, we'll try and put some of these things to test when we have a look and see the experiment. So let's go and have a look at what I've got set up. And here is what I've got so far. I've got a tube which is, I didn't measure it, probably about 3 centimeters in diameter, and this tube is slightly taller than I am, and Paul will just pan down now, and we can see that this tube basically goes all the way to the floor, and we've stuck it in a little bucket, and what I'm going to do is I'm going to fill that with water. Now Paul's sort of come up to my height again. We've got a rotation sensor at the top, and that's going to spin, and I'll work out what's going to happen there. We've got some string, and what I'm going to do is I'm going to connect that string to a small mass, and I've got in here some small masses. I've got ones like this, and we'll need to know what its mass is. We'll weigh it in a moment to see what it is, and I'm going to tie that to a piece of fairly thin string, and I'm hoping that this is actually going to be thick enough to make the wheel spin, but thin enough so that it's not going to be the major cause of drag on the system as it falls down. Now I have a feeling it probably will be, and I'm just going to tie this on, hopefully reasonably securely. Yeah, you can see that already it's not very secure. So I'll just try that again. It's not very nice. String. Right, let's have another go. This stuff seems to come undone quite easily. So it may have not been a particularly good buy. I'm hoping that will hold it. Let's do another little knot just to be sure. And I don't want the long piece sticking out, so we'll cut that off fairly short. Now what I can do is we can put this over the sensor, and that's going to be no good. I can see it's going to be no good because at the moment it's touching. So what I'm going to need to do is to move this around a little bit. Perhaps it is going down a little bit faster than I intended. Let's just try and tie that off a little bit. Let's just adjust this so the ball is now in the center. It's not going to touch anything. And it looks like we're nearly ready to go. Not held, that's a good thing. I normally tie a boat up with that knot, and since that one worked, I'm glad that is going to work. So we've got our object and it's going to fall. We've got plenty of string here, so it's going to work. And what I want to do is connect this up to some software. So let's have a look at the software. And I'm going to have to guess that this is number 4. Good, it's number 3. And we've got here some Pasco software. This is Capstone. And what we're going to do is we're going to have a look. So I've got my rotary motion sensor, and at the moment it's connected. And what I'm going to do is I'm going to grab hold of a couple of bits and pieces. So let's go and grab hold of a table, and what I want to do is I can measure various different things here, and we can decide what is the most useful thing to do. And I can measure its velocity, its position, its acceleration. Well, let's measure initially its velocity. Fortunately, this system will measure everything I need, and we can measure that against time. Let's also measure velocity against time, and we're nearly ready to go. The only thing that we've got missing now is some liquid, and what I'm hoping is, then what I've got is this watertight enough to play. So before we started, what I did was to set up the system. This is just a clear acrylic tube. It's still even got the stuff it came with. It's got an elastic band on it here, and the point of this elastic band was to try and put different elastic bands on and measure how well the velocity was going by just looking at them. I'm going to take them off because they're only going to confuse at the moment. So we've just got a bit of spiral band. It doesn't stop the experiment. It keeps the tube going a bit better. So I've got some liquid we're going to put in here. Then we're going to drop it and we're going to see how well it goes. But we've got to do several things before we get there. The first of these is I need to weigh my little mass so we actually know how much it's going to weigh. And I have a nasty feeling that when it hits the bottom it might come off, so we might have to use several different masses. I have come prepared. I have got several identical masses to sort of work on if we want to try and do this experiment several times. So what I'll do is I'll get Paul to get the balance over here quickly. That's it, thank you very much. And we've got a very simple balance. I'm not terribly bothered about the accuracy here because we know all these balls are supposed to be guaranteed to be 25 grams in mass, and if I put them on, I'm pleased to tell you that one was 25, that one was 25, and of course that one's 25 as well. So yep, they're all 25 grams, and I'm hoping they're all the same. So we've got 25 grams as our mass, and what we're going to do is we're going to fill this up with some water. Now if you have a look at this system, you'll notice that I've got a little problem trying to do this, and so what I'm going to do is I'm going to bring in my assistant to help fill this with water. So if you get a jug out, it's out already, above you, above you, above you, move your hand. No, there. Amazing how you can hide something in front of my son. Literally can't see where it is. Right, so we're going to try and fill this up with water, and I'm hoping it's not going to pour out too much. You think I can reach? I'm going to take the ball out of the way. I think it's going to make my life easier. I'm glad I'm doing this with water, not any other particular liquid. And I'm looking up, I'm not looking down to see if it's all pouring out at the bottom. My son's giving me a thumbs up. Right, so that managed to fill it up about a quarter of the way, and we are going to have to do this reasonably quickly because the water is coming out the other end. Not fast, but it is coming out the other end. The joint on here is very complex. I put a piece of cling film over the end and a bit of gaffer tape over that, and I can tell you that it is nearly waterproof. And that's why I've got the bucket there. Right, so we're probably 2/3 full.
Sorry, I don't understand.
And we're just losing a little bit at the bottom. I'll let Paul show you in a minute what we're losing. This is why I'm not wearing trousers today. I'm wearing my shorts. I don't fancy paddling. There. So we have our column, and it's got quite a lot of water in it, and we'll see how fast it's actually going down as we see, but it's got just a little bit of water coming out at the moment. So we're going to go reasonably quickly to try and work out what we're doing. Now the software wants me to have some indication here about how the rotary motion sensor is set up, and I've got to choose whether we're going to use the large pulley or whatever. So we're going to here use the large pulley. So I'm going to change the setup in a minute and let go. So we're going to set it up on the large pulley. No, we're not. I am. I'm going to get my little boy to come and change this onto the large pulley for me. And if we can put the ball in. Is it going to touch? Yes. Right. Put it on the medium pulley. Change plan. So what I'm going to do, wrong button, I'm going to put it on the medium pulley. So let's change our hardware setup here, and I'm going to use the medium pulley. That way the system will know what I'm doing. So we've got our medium pulley set up, and I'm going to start to record what happens. So I'm going to start the timer, and it's not doing very much at the moment. I'm going to hold on to this, and 3, 2, 1, go. And we'll stop and see what we've got. So let's have a look here. So we've got all my setting up and my wiggles before I got started. And let's just move that out the way, and then we can have a look at this, and we can see what's going on. Well, velocity certainly seemed to be increasing here. We've got a steady rate. It seemed to be slowing and then went faster. That's where it stopped. So we'll try it again and we'll see what happened. We can look at the acceleration here, and my acceleration started, went down, and then went back up again. So I think what we'll do is we'll reset this experiment and have another go and see if we can get any better results this time. I'm losing about 2 or 3 centimeters a minute. Right, so we're going to try this experiment slightly better this time. And what you can probably see, Paul's going to come out, he's going to show that I'm holding the string and ready to press the button. Right, here we go. So I'm going to hold it in the water. 3, 2, 1, go. Let's have a look and see what we got. Well, we've certainly got the velocity increasing, and then not doing much else. We are not reaching a terminal velocity here. We can see that gradually our velocity is getting gradually slower, looking at the figures here, when we sort of started, it's about 1.4, 1.3, 1.2, 1.1, 0.9. I'm going to need a longer tube, probably about 4 or 5 times longer, to try and see what's happening here if we're going to actually reach a terminal velocity. Well, let's try this one again, see if we get a few readings and see if we can get some better data.
I'm not sure.
So here's me pulling the thing up. Sorry, that required several of us in different places, and again my water level has gone down. I can see by the amount that's coming out. Right, so let's try again. Ready to record. Here we go. 3, 2, 1, go. And I'm certainly getting some anomalies here as I'm going along. We've got some clear acceleration and then it starts to slow. So it is doing something, but as to what it's doing, we can look at the position here, and the position is going from top to bottom quite happily. The distance wasn't getting any more. At around about 7.5 seconds it stopped. Let's look at the velocity. 7.5 seconds, so it was slowing. So we've got our increase in speed, and then it's starting to decrease in speed. So we've got our increase in velocity, we get our maximum velocity here, and then we've got it gradually slowing down until somewhere around here we're probably going to meet our terminal velocity. But we can see some sort of nice shape. I'm a little worried by this shape here. Perhaps another couple might give us some clarity on what's going on. I will refill the tube, I think. That will make some difference. I'm not yet paddling, this is good news. Take it nearly to the top. Right, let's, on this medium pulley, take this right up to the top. I can then, I want it just in the water so that it's not having a sort of an effect by going in the water. Let's get ready to have a go. So 3, no, we won't, we'll do it again. That was a false start. 3, 2, 1, go. And we are getting a suitable curve. It does seem to be a bit better that time. It seemed to flow better, and it gradually reaches here a maximum, and then when we've got our maximum here, just move that along a bit so we can see a bit better. We're getting our maximum velocity, and then the effect of the water is slowing it down, and that bit's where it's hitting the ground. So looking at our position, doing the same. There you can see our position, and it is slowing down as it gets to the bottom before it stops. So yeah, we are getting something. Well, let's do one more. So I'm going to look at the acceleration there. The acceleration increased, and then the acceleration is decreasing until it's nearly reaching zero. Maybe I need to get one of these tubes and join it to another one of these tubes. I'm reasonably happy with that one. Let's try again. What I'm trying to do is dry out the string each time. Right, making sure it's not going to catch on anything. I had a feeling it was going to catch. Let's do one more, and here we go. Setting the recorder going, and 3, 2, 1, go. And definitely not as good as last time. I think run 4 was probably our best look at this. Now, for technical reasons, what I'm now going to do is I'm going to demonstrate to you how to take the equipment to bits. And the reason I'm going to do that is I don't want to flood before we have a quick look at the results. So let's take this weight off. I was quite impressed that I didn't need to replace that string several times. In many other times I've done this experiment, we've had to do that. And what I'm just going to do is I'm going to perform the traditional yard of ale type of trick. This is not a yard, this is considerably more than that. What do you reckon we can do this in one go without getting things too wet? Right, so just leave that up there. Not too much water in there. I blame the person myself that put the cling film on and everything else. Oh, that was me. So I'll just tighten this just to hold it because I don't want a little accident to happen. And there, it's safe until I want to do the next thing. So, we had a go at an experiment here to try and work out terminal velocity, and it's failed. The way it goes on live stuff, but you know, it's just the way we sort of have to work with it. What we have seen is that looking at this, not for this run, but perhaps for a different run, looking at run 4, then here we have got a nice acceleration. We have got it reaching its maximum, and then we've got the effect of the water starting to slow this down, so we've got this upthrust. And looking at this on our acceleration, we can see the acceleration increase to a maximum, and then it was starting to decelerate, and we can see this curve starting to come in, and it was going to take a lot longer to come in and slow this down. So falling through water here is a problem. Now, what effect would it have had if I'd had less mass? Well, less mass is important. Looking at our equation here, we can see that mass would have had some effect on this, but here we're only trying some 25 grams, so we're not trying too much, and trying to find a smaller weight is remarkably difficult. I do have a smaller mass, and it's got a smaller area, and we might have got slightly better results from that one rather than this one, but not really, not significantly. So we've got our mass, we know the density of water is here 1, and we've got here our force of gravity, which is 9.8 meters per second. So we haven't got it minus much for the acceleration. It's just going down here by 1/25. If I put this in kilograms, which is a much better way of trying to organize this, then we could see that we're actually minusing only by a very small amount. So if I were to chuck you out of an aircraft, then you actually have to fall quite a long way before terminal velocity actually kicks in. And if you want to jump out of an aeroplane with a parachute, you've got to have enough height that that parachute's going to have enough effect to slow you down. So there are these fairly easy calculations that a parachute manufacturer would suggest that it's better to open your chute at this height, or this recommended minimum height, because that's the distance they know it's going to stop you. Yeah, you can open it later, and it is better probably than the alternative, which is not opening it at all. But if it hasn't slowed you down enough, then you're just going to go splat on the ground. We've had a little look then at free fall, terminal velocity, looking at what's going on, looking at how this liquid is sort of working, and we could here in theory try to work out at what point terminal velocity would actually kick in. So we can do that to try and work out a better way of doing it. Perhaps I'll leave you, if you want to to see if you can work out at what point and how long my tube would be before my object's going to reach terminal velocity. And you'll find it's actually a little bit longer than a couple of tubes. Anyway, if you liked what you did, I saw, good, please subscribe, and I will see you next week when we have a look at some more A-level physics, topic by topic. Take care. Bye bye.